to this talk about OpenOCD and hardware debugging and JTAG and such. I will talk about a short introduction, and I will talk about JTAG, how that works, what it is. I will talk about OpenOCD, how that works, and I will talk about how to use it. I will do some demonstrations. I've prepared 1.5 demonstrations. Let's see if maybe we can get them both working, or if it will just be the one. And I'll try to make some closing remarks. So my name is Peter Stuge. I grew up in Malmö, Sweden, and I moved to Berlin 2 years ago. I do software, hardware, security things, electronics and software development since I was a kid in the 80s, and open source really as soon as I discovered Linux since I think 95. OpenOCD I haven't been using for as long. I am one of the developers, but that doesn't mean that I know every single line of the code. I try to help out and fix things and try to do review and the other people when they say things that I don't like. But I also use it, and I start as a user like always. So JTAG. Hands up, how many have ever used JTAG? Okay, so why are you here? How many have ever used OpenOCD? Okay, so that's why you're here. Excellent. Okay, so this will be a refresher then. Joint test actually was a standard, de facto standard tool, I guess you call it. Some companies in the industry sat down together and figured out a good way to test new hardware that they made. So there was this, eventually there was an IEEE standard, this 1149.1, 1990 was the first one, called Test Access Port and Boundary Scan Architecture Blocking. It defines a bunch of signals. The 4 first ones are the most important, so the TCK, test block, TMS, test node select, TDI, data in, TO, data out, and the after reset is actually not necessarily required, but it's nice to have. So this standard's name is just a fancy name for a state machine that multiplexes various shift registers. So this is the state machine. How many recognize it? Okay, no. So the numbers, the ones and zeros, that's the TMS signal. And the state machine transitions on TCK. So depending on what level the TMS signal is, you will have the hardware moving around this state machine. So top left is the reset state. You can go from there to the idle state. Then you can go to the right to select DR, or one more step, you select IR. DR is the data register, IR is instruction register. But it's not a CPU instruction, it's a JTAG instruction. And in fact, a JTAG instruction is just a register number. So what happens here? Yeah, as I said, you set TMS the way you want it to make the state machine inside the hardware end up in the state where you need it to go. These shift registers, so both the instruction register and the data registers, they aren't fixed length. They're not really standardized. It's just the state machine that is standardized by JTAG. So every chip vendor has some different registers in their hardware. JTAG just says, okay, how can we move between these states? How can we talk to the shift registers, which is data. So this means that we really need to know what hardware we're talking to. That's very important because we need to know exactly what registers we're going to fill with what data to accomplish our goal. Here's some debugging. So here's an example of a typical setup sequence or a typical JTAG sequence. So the first step is here is TCK and TMS to go into shift IR. Now if we go back, see that shift IR is all the way over here. That means that if we're starting out from up here from the reset state, you have to go to idle, select ER scan, select IR scan, and you come to IR, and you shift IR. This is a bunch of clocks going out on the TCK line, and the TMS being set from the 3298 to this state, the shift IR state. Okay, next step is we scan in, as it's called, shift in. It's just the desired instruction, or as it is the register number, into IR in this shift IR state. So we do that by wiggling TCK again and setting the TDI signal to the correct bit that we want, while keeping TMS low. So we see here in the shift IR that if TMS is low, then it's going to stay in shift IR. So every time we clock something into TCK, there's another bit going into the IR register. And here's, of course, it's important that we know exactly how long is IR. Otherwise, we're going to be shifting a few bits or too many bits, and nothing will work. So when we're done with that, we here we go to the update IR state. So that's what actually latches the value that we shifted in and makes it effective inside this debug hardware. So we're here in shift IR, move on down to exit IR, possibly exit IR directly, and into update IR. When we enter update IR, hardware latches this register, the instruction is called register. And when that happens, we see here. So the register that we, the instruction that we sent, the register number that we want, is now connected to the TDI 0. So now this tab, the test access port, is disconnected from the instruction register and instead connected to the instruction or register. Instruction register or the register number that we told it. At this point, we are in update IR here. So now we want to put some data in this register that we selected. So we need to go into the shift IR state instead. Fill the data register or read from the data register. That's what we're doing. So we're here in update IR. We go somehow the shortest route you can select. Usually your implementations of this, you can select if you want to go the shortest route to the state or if you want to go some specific path into that state. Because sometimes the hardware components, they require you to go through the reset state. Let's take the shortest route. We go here. Oops, don't go to PR. Here, select PR scan, down, HR. At that point, we can then either scan in or scan out the data register that we initially selected. So, and again, here it's important to keep TMS at 0. As we see here, if TMS is 0, then shift DR, then the state machine stays in the shift DR state. For every clock cycle on TK, we're getting data that's in or out of both. So that's an example sequence. Is this readable? Let's see. Maybe if I zoom in a bit. So everyone loves the big award. I have here the reference manual for the OMAP processor on the WebC board. And looking into what it says about debug configuration here under chapter 25. So it says, yeah, you can use a debugger on this Cortex A8 CPU, and it lists the signals that are used. It mentions the target reset that we know, the test clock that we know. It includes RTCK, which is, yeah, this is a mixed blessing. It's a good and bad. It's a good idea. In practice, all of the so this is about ensuring that the clock that gets outputted output to the hardware is actually something that the hardware can use. Because when we're running a debugger, such as OpenOCD or something else, we can very easily say, okay, put TCK at 10 megahertz or 1 megahertz or whatever. But depending on the CPU, that's not necessarily going to work because the operations that we do inside this state machine, they have some effects on the rest of the hardware as well. Right? We're working with an instruction to poke around in the memory of the CPU bus. Then we need to match our timing. We can do, if the CPU bus is running very slowly, we can run very, very fast JTAG talk for TCK, because then the bus is not going to have any data for us when we start trying to shift out bits and nothing will work. So RTCK is intended to sort of handshake the clocking between the interface that I have my PC and the actual hardware that I want to run. So when TCK goes into non-asserted, the hardware is supposed to answer with RTCK and say, okay, now I'm ready, you can do the next clock cycle. It's a good idea. Unfortunately, it's not always implemented in the debugging interfaces, in the interfaces that you connect to the PC. In fact, it's very rarely implemented. So while in theory it's a good idea, in practice it doesn't really work so well. And this causes extra complications for us as users because now we have to configure a static clock frequency for TCK, and we have to make sure that it's really safe to use this clock frequency to talk to the tab that is very at every point in time we're using. So for, say, smaller microcontrollers, like the Cortex M3 that I have here, it doesn't necessarily start at full speed, and OLAP doesn't either. But the Cortex actually starts so slow that we have to use a really low JTAG talk TCK in order to be able to get it successfully in the beginning. And only after we switch up some ELLs we can increase the speed. But then we have to do all these things manually. We want to jump back and forth very easily. At least with OpenOCD, that's a little bit complicated. It requires quite advanced usage of OpenOCD. So for the simple use case, it's unfortunately the best recommendation is to set a slow fixed clock, and sort of live with well, not excellent performance for now. Any time anyone builds a excellent open hardware JTAG interface, which is really fast and commits or contributes to OpenOCD, there are some projects that are looking very good. So maybe TMS we know is the most select TDI. TDO, we also know the MU0, MU1. I haven't seen those on some other ARM chips, only on the TI chips. They select where the chip is moving from. There's usually some kind of mechanism, but it's not so common that it's sort of a part of the debugger. So nodes, power domain needs to be started properly before we do anything. So it says here applying a minimum of 10 TCK pulses after the tap reset is applied. So that's something also to keep in mind. Initialize the hardware sometimes probably in order to be able to take that off. So here it says yes, many test functions, test support functions. First level debug is the tap router module. So the tap is the name for this interface. This is part of the chip that has the state machine and its registers that you're talking bits into and out of. And here on the OMAP, there's a tap router module, as they call it. So it's here the debugger, the debugger, that's us, that's OpenOCD, and configure the tap router to serially link to 16 tap controllers, or we individually scan one tap controller without disrupting the instruction register of the other taps. That means inside the OLAP, there are actually not just one of these taps and one set of these instruction registers, but there are actually many of them. I don't know if it's 16. That sounds a bit much, but I know that there's at least 4 or 5 of them for different parts of the OMAP chip. It's a very highly chip with lots of things on it. There's the BSP and the CPU, and there's so what it says here is that we can sort of choose what we want to talk to by communicating with this tap router module. So it also says here the initial scan chain. The initial scan chain configuration is determined from the level of the EU0 and EU1 bits. Okay, so that explains my neighbor on the group together with other departments. They should be pulled high to configure the device into tap router only mode, so that we have nothing active in the device but this tap router. No secondary taps are selected. It's the only tap between the device levels pins TDI and TDO. So this in this default configuration it matches what I've said. But we don't want to just talk to this tap router. We want to talk to the actual CPU at some point. So it says the router tap has an IR length of 6 bits. So when the router is the only thing there, then the IR is 6 bits long, and adding taps to the scan chain is what we need to do. The tap router must be programmed to add taps to the scan chain. And there's a long list of what you need to do in order to get in touch with the CPU, in order to reach the CPU over this with the JTAG. So it says here you have some start parameters. It says send only IR/DR scan. Move shift state to shift IR, and destination is pause IR after it's done. Bit length is 6, so shift 6 bits out, and this is the data that it's supposed to send. Even zero padding is normal, so even if we're just sending the low 6 bits, sort of that, it's displayed here with lots of yeah, and the receive data is discarded because we write 6 bits without you send. And after that, it says to go shortest transition route into shift DR state, so around into the shift DR. And after that, after this shift is done, it should go to pause DR. We want to send 8 bits in, and we want to send bits 89. We don't care about what is coming back. We do another send scan, so another set of sending bits into this path. Going to the shift IR, shortest path, sending 6 bits, 02, POR address, not completely sure what that is. Send some bits into the DR, data register. After the data send, we pause. 32 bits this time, this magic, another magic value. And finally, back to shift IR. After shift IR, we want to go to the idle state, and by sending the 6 all ones bits, we end up back in well, the 6 all ones, and that's the instruction register to go back to nothing, or to the idle, and then the state is moved back to the main state. So after that, we talk in 10 pulses, as I said before. And at that point, there are some variables here saying that we need to, for any further communication that we do in order to reach the CPU that we just added to this scan chain, we need to have a post envelope of 6 bits. So anything we do needs to be followed by 6 bits that are for the tap router. So the first bits that we send will be for the CPU, and the last bits will be for the tap router. So we have the tap here, the CPU, and shift bits in the 6 bits for the tap router or the builder. On the instruction list, the data register is just 1 because we set the tap router into what is called a bypass mode. So that's just 1 bit large shift register. And finally, it says also the instruction register for the CPU here is 4 bits long, and the data register is at the moment 1 bit long. yeah, once we've done this dance, it says here after the dance, scan change the debugger processor, and here are addresses, and that's what we get from text customers. And OpenOCD does this already. The tab router is sometimes referred to as icepick, and if you want to, you can dig into the configuration files for the icepick and see what exactly is going on there, and it should match this description of this instruction. So the actual standards documents, very briefly, they included also the whole point of this thing was originally PCB testing. So testing the success of the yield of manufacturing, because the components that were beginning to become popular, they were not really testable with pros because they're packages. So there's this X test instruction that is also called boundary scan, which you may have heard of, and how many have actually used boundary scan already? Okay. It's a good idea. It's pretty nice. So this X test, you select the X test in the instruction register, and then you can use the data register to read and write from all the I/O things on the chip. And you can, of course, if you have a PCB with several different chips on it, they can be connected together. They should be connected together in the JTAG chain, and you can control them individually and set up inputs and outputs, and let some chip drive its signals. Then you can check from the other chip or on the other chip that actually the signals are arriving the way you want. Design. The revision in 1993, there was a revision of the standard. It adds two instructions called PLANT and IC. So the X test is only driving 0 or 1, and that was not so convenient maybe, because if you want to have one chip that just drives all its outputs, you have to ship a lot of extra bits. So they added this PLANT and IC instructions to be able to more efficiently just in bulk say some chip that okay, set all your bits to 1 or 0 or okay. Then there was the supplement to the standard in 94, which adds boundary scan description language for ESDL. This is a subset of the EHDL syntax. It defines what signals are on a package, the names. It defines IR instructions. They were previously documented by the vendor, but in non-standard format. In ESDL, you have a standardized format for these instructions, what you can do with them. And it also documents describes any extra registers that are included in among others, an optional 32-bit device ID register, which is handy, of course, for doing discovery of what kind of devices are on the JTAG chain. There's a public database at bsdl.info. I'm not sure if you may use it, but they have thousands of BSDL files for lots of different chips. Unfortunately, BSDL is not supported by OpenOCD at the moment. There's a line in the to-do file from 2009 sometime saying that maybe this would be a good idea to add, and maybe it would, but there's not at the moment some fitting user interface for it necessarily. What there is instead, however, is support for SVF, the scan vector format, which is sort of a high-level ASCII-based text format for doing very dumb remote control of a JTAG chain. So you have an SVF file that says, okay, scan out these bits into there, and I expect this result, or read bits from there, and they need to be matching this, or I don't care what they are, just read them and so on. So that's useful for production, for example. You can have an SVF player, such as OpenOCD or another software and hardware that does it, and takes your SVF file containing the hardware, the stuff that needs to go into hardware into some flash memory, and just have it play back in order to flash all the devices structure in an immediate way. So OpenOCD was part of Dominic Rath's development thesis in 2005. He's not active in the project anymore. I haven't actually, I don't think I've seen his name on any of this in a couple of years that I've been here, unfortunately. He was supervised in his work by Dr. Bergman, who also designed and built what is maybe the first open hardware, open USB JTAG interface using PDI chip, which has a bit of hardware acceleration to JTAG. So USB, before this there were parallel port-based dongles or interfaces. The Wiggler interface, maybe you've heard about, it's a common one. But unfortunately, my laptop doesn't have any parallel port, so I have to do something else. I like USB. As you might have guessed, I also wanted to use the project. So the USB JTAG interface was is kind of ubiquitous. It's the most common interface that we have, but it's a bit problematic also because, as we saw in the statement sheet, there's a lot of back and forth going on. There's a lot of sending bits, getting bits back, and USB has really awful round trip time. So you might have to wait up to a millisecond or even more to get a response from just one bit. If you are sending lots and lots of bits, flash 128 megabytes of NAND, then that is going to take way too long. So, yes, unfortunately, this FTDI chip, it does help a little bit, but it's still fairly round trip intensive, and that means that the cheap, the readily available USB interfaces for doing JTAG there, they do not have so fantastic performance. That's a bit of a shame. But there, as I said, there are some newcomers. There's the Black Magic interface that is looking pretty good, doing a SWD and JTAG implementation in microcontroller using more high-level protocol and communicating that micro USB. So that's the way to do it. Anyway, this Dr. Berger, this interface, I'm sure that it was an inspiration for many commercial interface manufacturers. There's a whole bunch of them based on pretty much the same design with some minor tweaks out there. And OpenOCD supports about 30 or so these FTDI-based. So this diagram on bottom, it's showing a bit of structure, well, the structure of OpenOCD. I hope it's visible, yeah, it looks good. So on the top we have a debugger, or something speaking GDB protocol. And we also have a telnet interface. So these are the two software components that are outside of OpenOCD that we want to use, that we have to use one of them. Inside OpenOCD we have this hard software. So that's the GDB server, the telnet server, working in parallel, talking to the JTAG engine. And all of this is, and the JTAG engine and proxy hardware abstraction, so it's being in parallel. The lower two layers, the JTAG engine and the hardware abstraction, that's all implemented using TCL. Well, no, sorry, it's not implemented using TCL. It's implemented in C, but you control using TCL. So OpenOCD uses the GIMP TCL interpreter. I don't know if it's used by any other project. Maybe it is. For a long time, it was the primary repository was OpenOCD for GIMP TCL, as far as I know. The GIMP TCL maintainer is also working with OpenOCD. It's a small, lightweight TCL interpreter. How many have used TCL before? Okay, yeah. Today I might have chosen something else, but it's there, and because of this telnet interface. So what you do is when you use the telnet interface, you can type commands to OpenOCD, but actually those commands, that's TCL code, which means that if someone has built anything that is using this telnet interface to remote control OpenOCD, then if we switch from TCL, then we need to make sure that it's really compatible with the old syntax that's the project, so for now, that's not. And I guess everyone is using that in the project for a while. So all the configuration files that are in and around, well, included in the OpenOCD package and are created around OpenOCD by users, they are in fact TCL scripts, even though it might just be a list of some commands. It could be a lot more elaborate, and some of the scripts or configuration files included in OpenOCD are pretty complex. So feel free to look into that if you want. The C code creates lots of TCL commands, obviously, which the configuration files call. There are configuration files for interfaces adapters. There's not really consistent naming of these, unfortunately. We need to clean that up really fast. Sometimes the connection between the PC and the microcontroller computer test is called interface. Sometimes we call it adapter. It's necessary in using. There are configuration files for CPUs. So the Cortex A8, Cortex M3, there are configuration files for chips, like the OMAP here on the keyboard or the luminary that I have. Motherboard targets, that's, what is that? What's that different from the chip? I'm not sure. And boards, finally, is the super component. So to say there's a configuration file for the TID board, there's a configuration file for this evaluation kit board. And the ideal way, in my opinion, the way I use OpenOCD is that I make a user configuration file. It can be called OpenOCD.config.cmd, and OpenOCD looks through this file, the current directory, when you start it up. The very minimum that you need to do with this file, and many times, actually all you need to do, is to reference one interface configuration that fits with a particular interface that you're using, and reference one existing board configuration for the particular development platform hardware that you're using. Now, of course, if you're making your own board, then you, depending on how much you change from an existing design that is already supported, you might have to make a copy of an existing config file and make some tweaks. Again, it's TCL, so it's easy to try out, and hopefully not so difficult. For a new board, you might want to change around some I/O signals controlling, let's say, a user button or some kind of angle signal for XR or peripheral that you use during debug or whatever. Obviously, the closer you are to the reference design, the less there is to it. Okay, let's see if I can do a demonstration. This one I think will work without much problems. This is a very bad photo of this setup. It's a luminary micro evaluation kit for Cortex M3. As I mentioned, it comes with this interface PCB, which is an FTDI-based design. And yeah, it's pretty nice. So let's see. I prepared a little bit. I have a configuration file for this board. Where we go? Yes, looks good. It sources interface FTI luminary dictic.cmd. So luminary dictic is the name of this. The name TI uses for this interface board, and then it sources the board / evaluation kit and then config for this particular evaluation. And what I'm going to do is I will start. First I'll show you what I have here. I have a couple of different directories. I have AP, which is the firmware that I'm running on this board. I have a bare box with the second demo. Beagle. I have a Beagle config. I have a luminary config. And finally, I have OpenOCD. So we have, as for releases, OpenOCD, we've been doing releases fairly infrequently, and I recommend to use the Git code whenever. That might sound really bad, and like any break all the time, but we try hard not to mess up the Git code, and it takes so many years for whatever we release today to make it into, say, Debian or Ubuntu, that please just use the Git code and talk to us if there are some problems so that we can get them fixed. In OpenOCD, since I'm just running this out of, let's see, I'll use this minute. I'm just running this out of I configured OpenOCD as such. I said configure enable MTDI because I want to use the MTDI driver. There's an older driver for these interfaces called FT2232. I leave you not to use that because the code is horrible. This FTDI driver is all new and shiny, and it's better performance, it's better code, it's less buggy, it's good stuff. So please use that. We haven't set it to the default yet for FTDI-based interfaces, but I will try to get that done pretty soon. And I also said enable DSL link for another interface that I have, and finally just prefix. But I didn't make install, so I just have the binaries here in source. This is my OpenOCD binary. So I want to start this. If I start this just like so, I get error debug that has to be specified as the interface command. And actually, I don't have to specify that interface command. I can just say lm3s my config file. And I get some other errors. It says can't find interface so in my lm3s. I'm calling this function find, and because I didn't do make install, I have to specify the path that it should search manually. But if you do make install, you just don't put it, and you set the path to wherever it installs the binary. This will not be necessary. Okay, so this looks better. Now I got a shiny little LED here. You see that in some of these configuration files, there's 500 kilohertz fixed frequency. We see that there's a tab found in the manufacturer, so the device ID is actually present in this device. And we see that the hardware has breakpoints and forward points. And now I can't do anything else here in this OpenOCD, where I started OpenOCD. It's not meant to run interactively. I can do two things. I can run GDB and connect to it, or I can run telnet and connect to it. So I'm going to do both. Port 4444. I'm connected. I can say help. I get a long list of everything we can do. And I want to eventually run GDB, but first of all, I want to do some flash operations. I want to do flash erase. Let's see. I have to say flash erase address. And there are two flash commands because there are two kinds of flash. There's NOR flash and there's NAND flash. NOR flash is, as you probably know, is easier to fetch instructions randomly. So it's used in the smaller, but it's more expensive. So it's only used in the smaller chips where you have less logic, and less. Also, you want to. The chip is running slower, so it's more important that the latency is high. The NOR flash operations are all done using flash commands. The NAND flash operations are all done using NAND commands. It's very intuitive. Again, with the compatibility for the TCL and so on, difficult to change this at this point, but let's see. Okay, I'm trying to do this flash erase address. I don't want to do any add and unlock is not necessary, but I have to put the address overlay. I know that the address is 0, but I still need to know the length. So when I say flash list, Yeah, okay, so OpenOCD knows that there is some kind of flash, but it says size 0, that's bogus. What I need to do to fix that is say flash probe, and I have to say ID also. And it finds a flash. I say flash list again, and now OpenOCD knows that this is actually 6K of flash. And it's on base 0, address 0, so let's try again. Flash base was it address 0 and length, so no, failed. Target not halted. Okay, so I need to halt. Very good, target state halted. CPU isn't running anymore. Let's try again. Yeah, okay, that worked. And if I do a reset init, I see again that the target state is halted. So the reset init does a reset of the CPU and all the peripherals. And it's supposed to start running again. What happens is it halts, and we see PC, the program counter is pointing here. This is a kind of exception handler because there's no firmware flash, so it's just going crazy. I will try to fix this by flashing the firmware to it, right image. And looking here, I notice also that there is a shortcut from what I just did. I can say flash right image erase as part of the write command. I chose to do them separately. To begin with, here is the path of the binary that I want to flash, and I don't have to say offset of that will work on its own. Okay, so this is taking a while. The file is is 104 kilobytes. Not so much. As I said, this is DDI stuff usually is not sports car. Yes, it does. And there is some code for it, but not all of it is there for using the RTCA. Please send patches. That would be fantastic. Yeah, so the throughput we got here was 3 kilobytes per second. Not so fun. But let's see if this works. So I reset it again. It's a demonstration, of course, that's fine. All right, so I'll try to, before I run out of time, I'll try to do the demo as well. Here I have a DB init file already, which says just connect to localhost and DB3, that's OpenOCD. So I say arm DB, and finally, with the debug symbols, is there. So, yes, we found that there is reset ISR somewhere. Monitor alt, I say load, that flashes from GDB through OpenOCD to flash to takes. Probably not necessary. Show another way of flashing. So when working in DB, it's more convenient to do it this way. Okay, the sign says stop. I want to set a breakpoint, and I want to say run. And yeah, okay. So here I am in main, and I can single step. I was hoping to be able to show also people looking at various memory addresses, but I guess all that I have. So, is there time for questions now, or no? Show me the stop sign again if you know. Yeah.
What do we need the board configuration file? Only the CPU.
So, what for example. Yeah. Memory needs to be initialized somehow, and that you work through it, whereas the chip, the processor chip will be initialized by the target processing unit and the CPU. Yep. All right, in the layer overview, where would yes. I see. Okay. So that is somehow in the JTAG engine. I would say. That's, yeah. So all of what OpenOCD really does with regard to talking to the chips is in the JTAG engine. No, I would say not, because we are also trying to get more frequent releases out. And of course, there are people by having some version. For using it, OpenOCD, have as the promise as possible. I would say to just get it. Actually, I would say that for any package, I'm big on using the data.
Yeah.